polar molecules like water, hydrogen chloride, etc. behave as permanent electric dipoles. Therefore, even in the absence of an external electric field, such molecules possess a permanent electric dipole moment. Non-polar molecules are those which do not possess a permanent dipole moment like the polar molecules. Hydrogen and carbon dioxide molecules are examples of such non-polar molecules. In such molecules, the average centers of the positive and negative charges coincide. Hence, they do not possess an electric dipole moment in the absence of external electric field. Now let us see what happens when a dielectric with non-polar molecules is placed in an external uniform electric field of strength E. Due to this uniform external electric field, the positive charges in the molecules are displaced in the direction of the electric field, and the negative charges in them are displaced in the opposite direction of the electric field. Therefore, in the dielectric with non-polar molecules, the molecules now possess some induced electric dipole moment, and it is said to be polarized due to the external electric field. Now let us consider the case when the dielectric material is made of polar molecules. In the absence of the external electric field E, the polar molecules in the dielectric are such that their electric dipole moments are randomly oriented due to thermal agitation, and hence the total dipole moment is zero. Now when they are placed in the uniform electric field of strength E, we know that every dipole in it experiences a torque, which rotates the dipoles in such a way that they align in the direction of the electric field. Thus, the dielectric material with the polar molecules is said to be polarized. The degree of alignment of the dipoles with the external electric field direction depends on the temperature and also on the external electric field strength. In general, the alignment increases with increasing electric field strength and also with decreasing temperature. Thus, we observe that the dielectric material is polarized irrespective of whether it is made of polar or non-polar molecules, and they develop a net electric dipole moment in the presence of an external electric field. Linear isotropic dielectrics are those in which the induced dipole moment is in the direction of the external electric field and is proportional to the external electric field strength. Now, when this linear isotropic dielectric is placed in a uniform electric field of strength E, it gets polarized. Let us consider the polarization P of such materials, which is defined as the electric dipole moment per unit volume. For linear isotropic dielectric materials in a uniform external electric field, the polarization P is equal to psi E into E, where psi E is the electric susceptibility of the material. Now each small volume element of the linear isotropic dielectric having a volume dV has a net polarization equal to PdV, due to all the dipoles in it in the direction of uniform electric field. Here, it is important to note that the net charge in each volume element will be zero. The resultant effect in the material due to the uniform external electric field will be the formation of an induced positive charge density plus sigma induced on the right face of the dielectric, and minus sigma induced on the left side of the dielectric. This in turn causes a weak electric field of strength E' to be induced in a direction opposite to that of the uniform electric field of strength E. Therefore, the net electric field E0 in the dielectric will be equal to E minus E'. Thus we observe that the polarization effect causes a decrease in the net electric field within the dielectric. Dielectric materials, being non-conducting, are useful in many devices like capacitors, transformers, etc. because of their inherent properties. Capacitors are devices that store electric charge. A capacitor essentially consists of a system of two conductors close to each other and separated by an insulating medium. The conductors can be of any arbitrary shape. Generally, the conductors are given equal and opposite charge of magnitude Q. This can be done by connecting them to the two terminals of a battery. The conductors carrying the charge are referred to as the plates. And because the plates are charged, an electric field of strength E exists between the plates. The potential due to the plate having excess positive charge plus Q on it is V1. The potential due to the plate having excess negative charge minus Q on it is V2. The positively charged plate is at a higher potential than the negatively charged plate. Therefore, V1 is greater than V2. Hence, a potential difference exists between the two plates. Let the potential difference between the plates be V equal to V1 minus V2. As potential difference is measured in volt, this potential difference is referred to as voltage. We see that the total charge on the capacitor is plus Q plus minus Q equal to 0, as the conductors have charges of equal and opposite magnitude. It is a common practice to refer to the magnitude of charge on the conductors as the charge on the capacitor equal to Q, and the potential difference between the plates of the capacitor as the potential of the capacitor V. The electric field strength in the region between the plates increases as the magnitude of the charge on each plate of the capacitor increases. Then, the potential difference between the plates also increases. Since the potential difference V between the plates increases linearly with the charge on the capacitor, Q and V are proportional. Hence, the ratio Q by V is equal to C, where C is a constant, which is the capacitance of the capacitor considered. Let this be equation 1. Capacitance C of a capacitor is its ability to store electric charge. Greater the capacitance C of a capacitor, greater is the charge it can store, and hence greater is the electrostatic potential energy. The capacitance C depends on the size, shape, distance between the plates and also the medium between the plates. The SI unit for capacitance C